Welcome to lecture 40 on risk management and insurance. In the last lecture, we discussed the independence copula and the Gauss copula. Now, in this lecture, we turn to the Gumbel copula. Now, unlike the Gauss copula, the Gumbel copula has a simple closed form. So we have a simple expression that gives us the Gumbel copula. I do it here for two variables. It's a bivariate Gumbel copula. With the Gauss copula, you don't have a simple expression like this. With the Gauss copula, you can write it down in the form of an integral, but okay, you will not have a closed form expression as we have it here in equation 36. Now, the Gumbel copula, we have the same notation as the Gauss one down here. So that's just a parameter of the copula. So here the theta, that's a parameter of the copula. Okay, it's up here, up here. Now, remember the Gauss copula was parameterized by the correlation matrix P. And if you had only two variables, then it was just the correlation coefficient. So here, because we have only two variables, we have here a single parameter, theta, which determines then the exact shape of the Gumbel copula. Now, if the parameter is equal 1, then the Gumbel copula becomes the independence copula. It's easy to do the math, plug in 1 here, 1 here, 1 here, then everything gets much easier up here. You get this here. And then actually this you can write down as a product of two Euler numbers here. The EXP stands for the Euler number, for the exponential number. And EXP to the ln u power is just the u. Okay, so the E and the ln actually are just offsetting each other. So the Gumbel copula with a parameter 1 is the independence copula. Let's go back and have a short look at the independence copula. Now here we began with the independence copula, and you see it's just a product of the u's. And now we look at the bivariate copula, so it's just u1 times u2. Remember, the u's, they are those uniformly distributed variables. When we apply the transformation, we have originally the x's, x1 up to xt. Okay, you have those observed value of the x's, and then you go through the marginal distribution. You take the CDF, the cumulative distribution function of the marginal distribution, and then you get the u's. That I think we had in equation 20. Yep, you see you have the initial x observations, and then you apply here the CDF of the marginal distribution, and then you get the u's, and the u's are the input in the copula. Those uniformly distributed variables, they are the inputs in the copula. U1 times U2 if you have only two variables. So the Gumbel copula becomes the independence copula if the parameter is equal 1. It's just here U1 times U2. Now, if the parameter increases, if theta increases, then the relationship between the two variables, x1 and x2, becomes more and more close. And the interaction becomes stronger. Remember, the u1 and the u2 are just transformed x1, x2 So a bigger value of the parameter here gives actually a stronger relationship between U1 and U2, and also between the original X1 and X2. Now on the next slide, we show a simulation of the gumball cupola in the left panel, and on the right, then we show the simulation of the original CDF with the X1s and X2. Now we assume we have a gumball cupola, but the marginal distributions are still normal. And we could take, as a marginal distributions, we could take a gamma distribution for the margin. So here we have those simulations. We assume the parameter of the gumball cupola equals 2. So here, that's a simulation of the cupola. Here we have the U1 and the U2. So U1 and the U2 are the inputs for the cupola. And then you can take this, so I do it 1,000 times. I do random draws 1,000 times. I take the axis and okay, then I'm simulating the cupola out of that. So I'm getting here pairs of U1s and U2s 1,000 times, and I plot that. And when you have those U's, okay, then you can transform that, go backwards to the axis. Remember, that's done through the inverse function, through the quantile function. And here then we have the simulated X1 and X2. If the cupola parameter is 2, and if actually the marginal distributions are normal. And what you see here is that's no longer looking normal. You see what we have here is actually we have upper tail dependence. If we have a high draw in X1, it's likely to have a high draw in X2. So two random variables are related in that sense. A large value of X1 makes it likely that we also have a large value of X2. We have this peak here. It's not a particularly extreme example, it can be more extreme, but down here we obviously have no peak. So this cupola, then the distribution of the original X1, X2 has actually upper tail dependence. It's not the Gaussian distribution. So that's what I summarize here. The gumball cupola with standard normal margins shows upper tail dependence. There is a greater tendency of X2 to be extreme when X1 is extreme, and vice versa. Now, naturally, if you think about returns to two shares, we may have upper tail dependence. You see, if one share has a high return, maybe then the other share also has a high return. They are related in this sense. So if you look at two shares in the same industry, maybe in the mining industry, they produce maybe iron ore. So if one company does well, probably the other company does also well, because the iron price is high, and this affects both companies. So this upper tail dependence actually may be quite important for shares, particularly if those shares are of companies in the same industry. And also insurance losses may exhibit upper tail dependence. So that's naturally important for the insurance company. If we have two types of insurance contracts, and if in one type of contract we have a high loss, then in the other type of contract it's also likely to have a high loss. That's important information for the insurance company. Then actually the two types of contracts do not provide a lot of diversification. Okay, so that's what we have here. Now, we have is a gumball cupola with upper tail dependence. There are a lot of types of cupolas. in my paper on quantity C, I'm actually searching over 40 types of copulas. So-called Clayton copula would have lower tail dependence. So actually, since the peak would be down here. And actually, the copulas can also go along a line like that. So there are a lot of types of copulas. Gumbel copula has upper tail dependence. Clayton copula has lower tail dependence. But I don't use now here the Clayton copula. And then naturally, the Gauss copula. Here we have it. Yeah, okay, we don't have tail dependence. So that's a Gaussian distribution with no tail dependence. Okay. So with the Gumbel, we have upper tail dependence. With the Clayton, we would have lower tail dependence. But the Clayton, I'm not using. Now, for the next topic, we need to know a bit something in statistics, the concept of the empirical CDF. And then actually we can use that, and we can discuss how do we estimate the parameters for the copulas. You see, in those two simulations that we did here, in this simulation of the Gumbel copula, I assumed that I know here the parameter of the copula. Also, in the simulation of the Gauss copula, I assumed I know, okay, that here the correlation is 0.7, which then is the parameter of the copula. Now, truly, you don't know. So you have to estimate those parameters. And so that's the next topic. How do we estimate those parameters of the copula? And so once you have the copula, you can use it for simulations. So we did it the other way around. We did here first a simulation because I wanted to show you the copula, how they look. And I assumed that we know the parameters. And now we discuss, okay, how do we estimate the parameters? In practical work, you go the other way around. You first have somehow to get the parameter. And then, okay, you can do the simulations. So let's make an example. I take it from the Rice book, which I have cited at the beginning. Okay, it's about beeswax wax. Okay, so about honeybees wax. Okay, so we have here some melting points of a sample with 59 different sources. And actually, say samples is to find out whether that bee wax is good or whether actually a bee wax is really far out and okay, maybe the producer of the honey is fraudulent and has actually put some cheap stuff into that bee wax. So they have here from 59 sources, they have sampled the bee wax and then they measured the melting points. So lowest melting point is 62.85 degrees. The highest one is 64.42. So lowest one on the lower axis here, I have here now those melting points, the temperature, 62.85. That's the lowest observation we have. The highest observation we have is something 64. Okay, that would be the highest observation. And so each observation we plot here, and we go up a step. So 62.85, and then you have the next one, and so on. Each one gives you a step. Sometimes a step is bigger, okay, because you have two observations. You see 63.3 appears here twice. So with 63.3, that's about here. Okay, we have here a step which is twice as high as actually those single steps here. That's because we have two observations. Now what we are doing here, we are ranking now those observations. So rank 1 is the number with the lowest value. So that's the rank 1. And then the rank 59, that's the observation with the highest melting point. So we rank them in ascending order. Okay, it goes up here, and then you have here 59. So we have now the rank of each of the observations, and this we divide now by the number of observations. So you would get here 59 divided by 59. Okay, yeah, okay, that's not entirely correct here. What we actually do, we divide 59 by 60. We divide it by n plus 1. You see, the rank, we divide it by n plus 1. Usually, you divide by n when you do the empirical CDF. Now we do n plus 1 because we want to avoid, okay, that we get the number 1. This would actually become a problem when we do the density calculations. So basically, you divide by n, okay, but actually we take n plus 1. But so we divide by 60, not 59. So we get here a little bit less than 1. In a standard empirical CDF, you would divide by 59 and then you have here a 1. Now, those numbers here along the axis here, they are uniformly distributed. You see, those numbers here are uniformly distributed. Those are those probabilities. They go from 0 here up to 1. So the probability that is that we have less than here this observation in rank 10, that's about 63 something. The probability is about 20%, 0.2. So that's a CDF. It's an empirical CDF. And the steps here are simply okay, the steps are given by equation 38. The rank, also note that, is the number of observations where you have a value of less or equal xj. So the rank, you see, is the rank number 10 is just the number, okay, where it's less or equal here 63 something, okay, it's okay, and that is 10. And you divide this by n plus 1. Now, since those pseudo observations, since those observations here, those U's here are uniformly distributed, we can actually now use those values in the copula. So those values here we can put into the copula. So that's an empirical CDF. You have all your observations here of melting points. You start with the lowest one, and then the next one is actually here pretty far away. Okay, and then it goes up, 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 up. If you have 2 observations, then it goes up a bigger step. If you have 3 observations or whatever, 4, then it goes up even a bigger step. Then here again, for quite a while, we don't have observations. So it goes up and up until you have all 59 observations. And by dividing by n or n plus 1, you get those numbers here. Those numbers are obviously lying between 0 and 1. They're lying between 0 and 1. And those are those U values, okay, which are uniformly distributed. Those are the functions values of the empirical CDF. And we can actually use those in the copula. Okay, I think now it should be more clear. And so rank is a number of observations where it's less or equals than xj. So the rank here, 10 is the number of observations where it's less or equal than here 63.4 or whatever it is here. Okay, we have here 10 observations. That gives us the rank. So that's actually quite a nice way of writing it here. Try to understand that one. Now, okay, we know now the empirical CDF. So we go now to fitting copulas to the data. So we now will try to find out how do we estimate a parameter like this. Okay, how do we estimate the copula parameter? Now the sample data include observations on d random variables for n time periods. So let's say d share prices, the returns to d shares, 1 up to d. And then we observe those returns over t years, maybe 20 years. So each year you have a vector with d observations. Each year you observe those returns to the shares, okay, this vector here, and then actually you have this vector n times. Okay, each year you have this data vector. And then that's very important. Let's assume that those data vectors are generated all by the same multivariate CDF, by the same joint distribution function. If that's not the case, okay, then naturally you're in trouble. So we assume that the probability distribution remains stable over those 20 years. If you have here a variation across time, then the problem becomes much more difficult. But okay, people work on that. This has to do with the concept also of stationarity, which is important in econometrics classes when you do time series analysis. Naturally, if you have here a fixed distribution, a fixed joint distribution over the 20 years, then the data are stationary. And those data, I said, are maybe different returns to shares. We have different d number of shares, or maybe we have d number of insurance products, and then those are the losses. So that's loss in year 1, then losses in year 2, and so on. We observe it maybe over 20 years. And the notation here again, it's a prime here. Okay, means okay, that I have here a row vector. So that's just a notation that's used, okay, in econometrics classes. They use for row vectors, they use a prime. Now, copulas are fitted by maximum likelihood estimation. You can read about maximum likelihood estimation in any statistics book. It's a very, very common procedure if you have not yet encountered it. So what you do, you do 2 steps. What you do first, you estimate the marginal CDFs and use them to construct uniformly distributed pseudo observations. You must get those U's. They are uniformly distributed. So you get this vector of uniformly distributed pseudo observations. So somehow estimate the marginal CDFs and use them to construct those U's which you need as inputs in the copula. And then when use those U in the copula and estimate the parameter, okay, of the copula. And that's done then by maximum likelihood. So 2 steps. First, get the use. Okay, the vector of the use, and then get then use them to estimate the copula parameter. Now, the use you can get in 2 ways. One I have already explained. You can do it in a so-called non-parametric fashion. So just use the empirical CDF, as I just have explained before. So it's based on the rank of an observation. So do those things, do those for the marginal distributions. I have the axis here for the marginal distributions, and then actually just measure here the use, get the use. They are uniformly distributed. They lie between 0 and 1 with uniform distribution, and you can use them in the copula. So we can base actually, we can just take this, we can just simply take the empirical CDF of the marginal distributions. It's very easy to do. What you also can do, actually, you can do a parametric estimation. So you could actually, for your marginal distributions, you could choose a special distribution function, maybe a Gaussian one or maybe a gamma one, and okay, just try to fit it. And then use the fitted model for the marginal distribution to calculate the use. And then again, put this into the copula in the second step and get the parameter of the copula. Also here, you will use probably maximum likelihood. So parametric estimation, here we make an assumption on the marginal distribution. If the assumption is right, we get here actually the better results. But naturally, if the assumption we make on the marginal distribution is wrong, then we make a serious error here. If we take here a gamma distribution and we should take another distribution, maybe a t distribution, then we make a serious error. So that's a bit more risky, but actually it's more efficient. Okay, you get the best result if you are right, if you apply the right distribution. Now with non-parametric, okay, you don't make a mistake, but okay, it's a little bit less efficient, and particularly the CDFs are quite unreliable in the tails, so the empirical CDFs. This may cause you problems because we are particularly interested in the tails. You see here up in the tail here, okay, we don't observe here much. The extreme values we don't observe much. Maybe if we do a lot more testing, then you would also observe a value here, but that's not shown because our sample is only 59. If you get the larger and larger samples, and maybe then we get here a slimmer tail, and also down here. So the tails are not particularly exact. It depends actually on the sample size. If it's over time, we said that, okay, then maybe you said those extreme observations you do only every 100 years. But okay, your insurance company is only 20 years old. So you have never made those observations. That's what we did, okay, when we did actually this normal power approximation. Okay, that's a big problem here. Okay, those tails. And it's too bad because we are actually interested in the tails. You see, we as insurance companies naturally interested in extreme events when it needs when there are huge losses. Okay, so fitting copulas to the data. Let's first get those marginal CDFs and okay, get the use and take those use, okay, and use them to estimate to fit a special type of copula. So you must actually here select the copula type. Here, okay, this would be for Gumbel copula. Naturally, if the parameter for the Gauss copula would be the correlation coefficient. Okay, that's different copulas naturally have different parameters. So here you must make the assumption which copula to take. And then you fit it. You could actually fit different types of copulas and then just look what works best. Okay, that's naturally done. Okay, and there's just fit 3, 4, 5 types of copulas and look where you have the best fit. And then you will take that copula. That's what I do in that paper on the quantity theory. Okay, that's just that paper I gave recently in March. I gave a seminar on this topic. Now, I will not repeat the seminar here. I just show you a few slides out of that seminar, and then maybe you read this article here. Okay, it's available on SSRN. You get the article free. You don't have to pay for it. Okay, just give this into your browser and then go to the article. This article is easier than what I have done now here in class. And it looks at it from a little bit different point of view at the copulas. So it would be really worthwhile. You have here a first introduction. I gave you a first introduction to copulas here in this class. But then here you have an easier presentation. But it also gives you a different point of view. So it would be worth